Alright, so this is the introduction of 4.5b, talking through the rational roots theorem and factoring polynomials. So, the new piece that we need to talk through is what is that rational roots theorem. So we factored out polynomials before by finding greatest common factors, using factorial patterns, using grouping, different types. So what happens if you come up against a problem that you cannot use any of those typical patterns? So we have a rational root theorem. This allows us to factor out things that seem unfactorable. The rational root theorem is a starting point. It's a way to find factors without using any of the other patterns. It's a brand new thing. So it is based off of a little formula. That formula is, and I'm going to do this because it's important, plus or minus, because remember, like our conjugate theorems, there are always two sides to these factors, plus or minus P over Q. Now for the rational root theorem, the P and Q represent information. P represents all of the factors of the constant term. Q represents all of the factors of the leading coefficient. So rational root theorem allows us to create this set of possible roots or possible zeros. It does not give us all of the true ones. It only gives us possible rational solutions. Also, because this is a rational root theorem, it does not give us irrationals or imaginary solutions. It literally creates this big set of possible rational solutions. It allows you to test these solutions, see which ones are truly zeros, and then continue to factor out other parts of the polynomial. When you use the rational root theorem, you are going to use another theorem, and it's called a factor theorem. The factor theorem uses synthetic division to test. We will create this list of possible rational solutions. We're going to use synthetic division to test it to see if it's an actual zero and it will actually create a factor or not. So, super incredibly important. After we do this list, when you test with synthetic division, a true zero will end with a remainder of 0. Okay? So after, that should be an R, synthetic division, if your remainder is 0, then you get to do a big yes. It's a true 0, which can make a factor. Okay, so we're going to just look a little bit right now at the rational root theorem and kind of do some proving of why it's true, all that good stuff. So let's go through some prior knowledge. So just a little reminder example for us. So if I asked you to completely factor x cubed minus 3x squared minus 4x minus 12 equals 0, and then explain what those factors represent, and we're going to see, do the factors that we find follow the guidelines of the rational root theorem? So we're going to factor it with things that we already know how to do. And then I'm going to show you what we would do if we use the rational root theorem to prove to you why this list has what we need in it. All right, so it'll kind of make sense as we walk through it. So I'm going to start with my x cubed plus 3x squared minus 4x minus 12. Right? I don't want to factor it, so just with the things that I already know. So let's start by asking, is there a greatest common factor out of all 4 terms. Can I divide an x out of all 4 terms? No, because the 12 doesn't have an x. Can I factor a whole number out of all 4 terms? Well, that x cubed has a 1 in front of it. So if your greatest common factor is 1, not super helpful. So what is it? One of the other things, if you have 4 terms in your polynomial, you can use grouping. So I'm going to look at the left side and look at the right side and see what I can find. So when I look at the left side, I can find a greatest common factor of x squared, and if I divide that out, I have x plus 3. And if I look at the right side and I find myself a greatest common factor, I see that I can take out a -4 and be left with x plus 3. Oh, look at that. My factors match. That's exactly what I was hoping for. So I can rewrite that. So I'm going to take those. That is one factor, x plus 3. And I'm going to take my greatest common factors, and they become x squared minus 4. All right, so x squared minus 4. Oh, that is the difference of squares. So that actually breaks out into 2 pieces. X plus 2, x minus 2, and I keep what I already have, x plus 3. So that's factored form. All right? So now, when I look at it, I'm going to look at it in a different way, and I'm going to say, okay, what does this represent? Does it follow the guidelines of the rational root theorem? Well, these factors represent pieces of my polynomial, and I can use them to find the zeros. So what are your zeros? I have -2, +2, and -3. So these are my zeros. These are my x values that would cause a 0 in my function. If we were using the rational root theorem, this is what it would look like. I would take my polynomial, so I would take my x cubed plus 3x squared minus 4x minus 12. There's a 1 right here. All right, so my lead coefficient is 1. My constant is -12, and it actually doesn't matter if it's a +12 or -12 because that plus or minus in front of the p over q term will kind of negate that in the end anyways. So if I do plus or minus factors of p over factors of q, so factors of 12. All right, so 1, 2, 3, 4, 12. Factors of 1, that's easy, that's 1. So we're going to create this list. So our possible, so they're not all true, and it's only the rational ones, so possible rational solutions or zeros. We got positive and -1, positive and -2, positive and -3, positive -4, positive or -12. So I'm going to look at what I got on the left. See, I got -2, +2, -3. Oh yeah, here's my positive and -2, and in this term is my -3. So what it is this rational root theorem is going to create this set for us, and we're going to test that set to find out which terms in that set are zeros and would create factors. We're going to use synthetic division to do that. Hey, just so you know, these can tend to be really long problems. It is not that they're overcomplicated. They actually are really simple steps to do, but because of the process of testing, they can take a long time. So just be aware of that and go slowly, take your time, And as we work through this lesson, I'm going to give you little tricks and things that I do that tend to make it a smoother process.